Okay, here we're going to work through the longer answer questions. So we're starting with this falling block. So we have an elastic climbing rope tested by fixing one end to the rope to the top of a crane. The other end of the rope is connected to a block, which is in position A. The block is released from rest. The mass of the rope is negligible. Okay, so 1A, show that the speed of the block at position B is 34.3 meters per second. So we know that S equals 34.3. We know that A equals 9.81. We know that U is 0, and we know that V is what we're trying to find. So we want something relating these quantities. So we'll use V squared equals U squared plus 2AS. So V is going to be equal to the square root of 2 times 9.81 times the distance that it's moved, which was 34.3. No, sorry, that's not S. S is 60 times 60, which gives us, so 2 times 9.8 times 60, then we'll take the square root and we get 34.29. Okay. 1B. At position C, the speed of the block reaches 0. The time taken for the block to fall between B and C is 0.759 and the mass of the block is 80 kilograms. Find the magnitude of the average resultant force acting on the block. Okay, so I'll just number these. This is 1A. This is 1B. We know that the force is equal to the rate of change of momentum. And in this case, we can figure out what the change in momentum is. We can say delta P is equal to PF minus PI, which is equal to 0 minus what was our initial one? 34.3 is what it had at B, right? Minus 80 times 34.3, which is equal to 2,744. And therefore the force is equal to 2,744 over the time that was given, which was 0.759. So we want to divide this by 0.759 and we get 3,615 newtons. And we were given things to 3 significant figures, so we should really give our answer to that as well. So it's 3.62 times 10 to the 3 newtons. Okay, so we've done A, we've done B. C says state the direction of the average resultant force acting on the block between B and C. Well, in fact, this should have been negative, this should have been negative, this should have been negative. So the negative sign means it's in the opposite direction to the direction that the speed was, so it's going to be upwards. So 1C is upwards. And D, calculate the magnitude of the average force exerted by the rope on the block between B and C. Well, if we've got the block, we know that the net force is going to be this minus that, where this is Fg and this is F rope, and we know then that F rope minus Fg must be equal to the net force, which we've worked out, which is 3615 newtons. So F rope, is equal to 3615 minus 80 times 9.81. Sorry, plus, which is, so we want to add to this 9.81 times 80, which gives us 4,400 newtons, or 4.40 times 10 to the 3 newtons. So this is question number 1D. And 1E, for the rope and block, describe the energy changes that take place between A and B. And there's only one mark, so we can just say what change happens. So between A and B, it's just gravitational potential energy to kinetic energy if we can ignore friction. So we can say, ignoring friction, ignoring air resistance, it is from gravitational potential energy is converted to kinetic energy. If we wanted to include friction, then we would say that some heat would also be produced. So some of the gravitational potential energy would become heat. 1F is between B and C. So the main change between B and C is that the rope is stretching. So we're getting kinetic energy and gravitational potential energy is being lost. So kinetic energy and gravitational potential energy is being converted to elastic potential energy. In the rope. It will also produce some heat. In the rope. It's only one mark, so I'm guessing that that last little bit is not required. 1G says the length reached by the ropes at C is 77.4 meters. Suggest how energy considerations could be used to determine the elastic constant of the rope. Okay, so it's only 2 marks, and it says suggest, so we're not asked to calculate it, but we could. So we can say that 1G, total energy lost, will be mg delta h, because it started off with only potential energy. By the bottom it will have lost all of its kinetic energy, so the energy that's been lost is just the total gravitational potential energy lost. So that's going to be 80 times 9.81 times 77.4. At the bottom, this is all elastic potential energy. EPE equals half times K times X squared. So if we knew the spring constant, we could, oh no, that's what we're trying to find out. So we would equate these. So we would go mg delta h is equal to 1/2 kx squared, and solve for k. I don't know why they didn't ask you to do it, because it's doable. So we get k is what we're trying to find. K is equal to 2 mg delta h over x squared. So, and we might as well do it since it's doable. Equals 2 times 80 times 9.81 times 77.4, and we divide that all by x squared. Sorry, not 77.4. Oh no, it is 77.4. That's how far it's fallen. And we want to divide it by how much longer it's gotten since it started stretching, which is 77.4 minus 60, all squared. Because 60 was the unstretched length. That was the length that it was before it started producing a force. So that would give us k. And why don't we just work it out since we're here? Note that the command term suggest means that you don't have to actually find the solution, you just have to say how to do it. So 2 times 80 times 9.81 times 77.4 divided by 77.4 minus 60 squared, which gives us 401 newtons per meter. Okay, so doable, you probably only needed to say this bit. And you probably didn't even need to include any numbers since it was suggest. Cool. Okay, so that's question 1. I'll do a separate video for question 2.